So, as you know, so I'm filling in for Bill Chrysler. So this presentation will be a little bit bifurcated. He gave me a set of slides. I'll speak to them, and then I'll follow up with a bunch of the work that I did there, which actually now has been almost 10 years that I've been at Bentley Systems, first in generative design and now kind of running our flagship product, MicroStation. So I'll just launch right into it. So you'll see composites have made quite an impact in a lot of industries, and they've found some really good application in things like, windmill blades and boats because of the ability to take certain shapes and be resistant to difficult environments like salt water. High performance materials like carbon fiber for pole vaulting and for sailboats. And in industrial applications, these big tanks wound on a mandrel. But what's missing from this, obviously, is buildings. And it's a shame because the building industry is really big. So there's a tremendous opportunity for the use of composites in architecture. But there's a bunch of reasons why they aren't. And knowing them, thinking about them a little bit, helps open up the possibility to change this stuff. So one thing about the building industry, as you know, or will come to find out when you go to build buildings, is that they're built a lot like movies are made, where a guy knows another guy, he knows another guy, and pretty soon 300 people are working on a project together that have never seen each other before, and when they're done, they go away and never work with each other again. And so it's a fragmented industry. It's subject to varying different kinds of methods of construction by geography, by the politics of the jurisdiction, and all sorts of stuff like that. And it's also built to resist change because municipalities and stuff are very risk averse, and the governing bodies themselves are governed as much by anything from politics and moneyed interest to councils of people, and you go and plead your case, and they kind of protect entrenched industries too. So getting architectural applications of composites has been slow going. One of the problems is that the building industry lags behind lots of other industries in its actual research. This little chart showing, the share of R&D by different industries across a bunch of countries, and you'll see, here is the top 2,500. Here's the U.S. So there's a lot of work to be done there, just in terms of the basic research into application of new materials. And a little bit of the call to action, which is that as an industry, the building industry is terribly inefficient and has fallen off the curve in terms of productivity gains. So, well, why would that matter? I mean, if your firm stays in business and whatnot, like, why should we want it to be more efficient? One of the reasons is that buildings themselves are really inefficient. And so there are lots of problems to solve, and architectural composites are very uniquely suited for some particular problems in buildings. So a couple of things about composites. They're incredibly strong, but in a particular way. So this specific strength is sort of strength to weight ratio. So they are very strong for how much they weigh. And just comparing them to steel. Carbon fiber is like the famous one, but glass fiber actually isn't that much worse. It's not quite as stiff, but it's a lot less expensive. So you won't find carbon fiber used much in buildings outside of some of its particular properties. The thing to know here, it's not on the chart, but keep in mind, the other thing is modulus of elasticity, which is like how stiff things are. Steel is really stiff. composites can be pretty bendy. And so the trick is to combine the two and to speak to the different properties of the two materials and smartly design composites actually being the resin, the cloth, and the structural reinforcing in it. So Bill Chrysler and has been a board member, a former president of the ACMA, which is the composite kind of like a body, right? They've written this guide, and it informs the building codes, and it's beginning to be accepted. So you are now seeing, large-scale application of composites in buildings outside of, the anomalies. So I'll show you a few projects that are that are like in construction or constructed as some examples of good uses of composites. This is a 1000 museum Zaha building in Miami. And in this case, the design team took, they wanted a composite, so this shell here is composites, right? And the proposal was this backup structure, right? Because you need it because it's going to be really wet and humid in this room. And so the drawings that they brought to Chrysler and Associates showed this steel frame on the left. But one of the difficulties, and I'll say this again and again in this presentation, is that this is a material very much unlike most of the other things that the architects have any experience with. So the designs for them can be really, well-meaning but very naive, right? You don't need this kind of structure. The panels themselves are strong. So with a little bit of finite element analysis, they got it down to this drawing where you can see the panels span and there's nothing but the kicker, so it's only supported in one place. And the panels have shape to them, so they resist flexing, and off you go. And you saved both construction time and you saved a great deal of steel, which not only do you have to buy, but you also have to support with the rest of the building. This building also shows a much larger version of the same lesson. This is the San Francisco Museum of Modern Art by Suico, and the contractor is Webcor. And with Enclose, Chrysler and Associates did this facade. And, one of the big challenges in composites in buildings is fire resistance. It's a combustible material. You can control it, but you can't get away from it completely. And so sometimes you'll see a glass fiber reinforced concrete, GFRC, rather than fiber reinforced plastic, FRP. I'll use those, FRP. It's an easier way to say it. But some of the things about this building, it was originally designed by Suico to have GFRC panels because of the fire resistance and because of the familiarity of working with concrete. But GFRC is not strong in the same way that fiberglass is. It wants to crack, so you need a steel structure behind it. So by using FRP, the panels themselves are so much lighter and so much more structural that you don't need a steel backup structure. So they were actually going to have the weather wall, an air gap, an outboard steel structure to support a set of GFRC panels. By eliminating the exterior steel, see, the FRP weighs like 3.5 pounds a square foot, and the GFRC weighs something like 15 pounds a square foot. So not only do you save a steel backup structure, but you also don't have to carry that weight through the structure of the building. So it was a savings of millions of dollars, not just on the panels themselves, but on the backup structure. It's the weight of the thing. And after the fact, the structural engineers realized that they could have, they much over-designed the primary structure of the building based on GFRC. And there's the tower crane can reach farther, so you don't have to move the tower crane or build as big of a tower crane. And because you can take the Enclosed did modular panels, the FRP is not separate, it's with the interior panels. So the Webcor only had to go around the building one time. The whole facade was put on in a single piece. So in a congested site in downtown San Francisco, you don't have to stage something twice. You don't have trades running into each other. So oftentimes it's the system effect of using a material like this where its efficiency comes, because it might be more difficult to do in some ways, but you just have to know where to apply it. A couple of other applications. Here's the Bing Concert Hall. All of the interior panels are FRP, and they're backed up with concrete, so they pour concrete into the molds before they're demolded in order to get the acoustic performance of the panels. This is the Monterey Bay Aquarium, and the interior of this enclosure for sharks, I think, is fiber reinforced glass. It's glass fiber reinforced polymer. And instead of filling the resin with talc, as is often done to make it softer and more workable and less expensive, it was filled with a harder mineral so that it can stand up to the scrubbing that needs to be done on the inside of tanks. So the material itself can take on a great number of characteristics by what you do with the resin. So a few projects that are in proposal or on the books or in construction. This is a rendering of a boathouse in Tulsa. And oddly, Bill said this is one of the most difficult projects that they have ever done, because this wireframe this is a rendering. That wasn't built. So all that's actually there are the columns and the panels, which means the panels span a couple of bays between columns. So the panel joints are structural, like semi-structural, and so they're having to figure out all the deformations of it. No two panels are the same. So you can make this stuff as complicated as you want. Another interesting project, this project went on for a great while. I was at Chrysler & Associates during the time it was in design, and they finished it just after I left. This is a private residence on an island in the bay, and it's a monocoque structure, so there's no interior structure. If you went down into the hull of a boat, you wouldn't find columns, right? It's the shell of the boat is the structure of the boat. So like the piece on the right, if you flipped it upside down, it would float. It's like that. It's like a single fiberglass structure. So you can do monocoques if you're able to design them and if you're able to get them permitted. This is just a research project done at CCA. And what they discovered here was that you can take and get different kinds of marine organisms to grow by the shape of the shape of the underside of this piece. A piece by Aka Menges, I think it's a pavilion in Stuttgart, and these are ETF panels. I think they're thermoformed, and then he's laying the fiber, this is like carbon fiber tape placed by this robot arm on the inside, using the bubble as a formwork, inspired by, I think, these spiders that blow little bubbles and then build a web inside them. So it's a very adaptable material that can be placed, you can put the structure exactly where you need it. That's, I think, the lesson in this, right? One of the many lessons. And this is a project that's on the books. It's going to get built, the Lucas Museum of Narrative Arts. And I wish these renderings showed more closely the surface finish, because it's going to be essentially a glass terrazzo. So the gel coat of the, we'll get into what gel coat is in just a second. The gel coat is going to be glass and then done like terrazzo, so the whole thing will have a real shine to it. The rendering actually is sort of accurate in that case. And Tom Wiscombe's boneless chicken, again, why have an interior structure when the shape of the thing and the panels themselves can be strong? especially when you want to put this on the roof of a parking garage and the structure, the existing structure isn't built to carry the dead load of another building. Well, then the building needs to be as light as an airplane or a boat. So now for the benefit of those of you who haven't spent a bunch of time in a composite shop, I'm going to go through some projects in kind of gory detail to show you what's involved in them, the kind of combination of the real high tech and the high touch. So this first project is it's a lantern. This cocoon-shaped thing in the lower right is a lantern for this house in Southern California. And this is the drawing that was done. And it just shows this kind of typical thing where, so here's the composites, and here is this clip with a piece of dead wood in there to join the two pieces. It would cast a shadow and these huge clips. And it's just not necessary. That kind of construction isn't actually how you build them. What you do really is you use flanges. A real convenient thing is to have keys between the flanges so the panels line up. And especially if you cast one panel against the other panel, they fit perfectly. You build them together, you take it apart, you put it on site, and then they go right back together. So took the lantern, sliced it up into its component pieces, splayed it. Then those are the flanges to the outside so that you can get to them and assemble it. So it's just one view of it. Chop it up, and then, it's interesting how much modeling contractors and fabricators actually have to do. In this case, there was more modeling of the thing around the thing. So the form work for some of the individual pieces milled up. Here's the piece, different parts of it before they've been trimmed. And then the production run of the molds. So you'll see this technique a few times. So I want to give away a secret. You can use this one. So polyester resin has as one of its component parts styrene. The white stuff is expanded polystyrene foam, which means your polyester resin will eat it like you were pouring gasoline into a styrofoam cup. However, spray mount and a roll of aluminum foil from the grocery store is enough to protect the EPS from the resin long enough for the resin to kick. And all it leaves is these paper-thin joint lines between the pieces of aluminum foil, which you can buff out if you need to. And you saw by the size of the pieces, the cost of the foam is a significant part of the mold making. So off you go, a whole lot of foil. Sprayed with the PVA release agent. It's cold enough in the North Bay area where the shop is, just south of Napa, that you need to heat the pieces up to get the resin to kick in the winter. And there they are. Now, let me take a quick digression about this. So it's a lantern, and Greg Lynn, you can imagine, has a very finely honed aesthetic. And the fabricator's in the job of finding a thing which matches that aesthetic. However, it's an interior piece, and it has to look perfect. But walk outside, and we had leaning against the shop this piece. So this was like, the Greg Lynn piece was probably $15 a square foot, and this piece might be $2 a square foot. And the difference is the quality of the glass, the amount of time you took, these intumescent coatings on it and stuff. So if you're willing to take something that looks like this, you can drastically reduce the cost, but you have to kind of know the aesthetic of it, like how the cloth is going to be laid in it, as opposed to, like the lantern, have to take the little pieces and tear them all, take the cloth and tear it into all these little pieces and put it into the mold so that there aren't the lines of the strips of the glass cloth put into the mold. So Here's some shots of the completed lantern. I guess the whole talk, maybe every talk, is a digression on something. Here's another really interesting technique I just want to share with you, just the reminder about how much pressure the atmosphere can apply on something. Kind of steal from, using veneers for furniture making. This was a canopy that we did for, let's see here, a prototype canopy for a large coffee company to cover their drive-thrus. Didn't go through, but we made this one prototype. And one of the challenges is to make flat panels rigid, you have to put a core in them. And to get the core to bend to a curve is difficult. So in this case, it's a bunch of shop vacs and visqueen to just vacuum bag it using a plastic from Home Depot, essentially. The rope is in there to let the air escape and be collected up by the vacuums. So it's makeshift is kind of the point there, right? There were half a dozen shop vacs running simultaneously to pull enough vacuum on it. But the shop vacs and visqueen from Home Depot, just like you could use in the studio. So much of, one of the things about composites is that it might be one of these last frontiers where a lot of the tools and techniques that go into it are like at your fingertips. They're things that you could do and stuff that you could buy. I guess at the time this machine was constructed, maybe it was at the limit of what you could do now, especially with where DIY has gotten to and rep wrap and Arduinos and stuff. A lot more servo control stuff is like right out in the open. But it really struck me when I came to Chrysler & Associates. This is a machine that was there when I got there. This is a vertical mill. You might just like to know what this thing is, actually. So we've got X, Y, and then Z is turning the table. Roughly hewn steel structure, counterweight from the sporting goods store. And the bearing was a salvaged bearing from an old crane. And you can only imagine how much slop there is between that bearing and the pinion gear that runs it. Despite forcing the pinion gear so far into it, it distorted the plastic. But the trick there, of course, is you don't have any backlash if you only ever run it one direction. So always spiral it around the one way. And even at 8 feet in diameter, we could get it down to about 1/8 of an inch in tolerance. So, is that good enough? Well, it turns out for artists, it is. So the side business at Chrysler & Associates, especially at the time before, there was a certain time in foundry where it was really hard to get these, to go from a maquette, a small, carved wax or clay. We would laser scan them, and then we would use this machine to mill them out. So that's like twice life size. And then we'd send them to foundries to be turned into bronze. And it was interesting because we sharpened our tools on a lot of curvaceous kind of forms that were making their way into architecture. Turns out to be a lot of the same techniques. So some of the content was a little like, do I want to really do another equestrian? But actually, you can learn a lot from that. And one of the things that I learned was making the tolerances of the techniques suited to the budget of the artist or the architect. Because this machine could not mill a turbine blade. It's not precise enough. But if you go to an aerospace manufacturer, they're going to charge you, $250 an hour to run their mill. I can run that thing for $50 an hour. So it's definitely about making your own tools. It's how I met Bill Chrysler and came to work there. Today is probably a very unusual day. Alexander, this is probably the first and last time that sand printers have been shown twice in one night. This is a project that I did as a collaboration at the studio at SIGGRAPH, and it's how I met Bill. They built the rig, and I wrote some code to turn images. into pixels and then write them out using G-code so that this machine can understand them. Again, avoid the slicer and go directly to the code, because you can do funny things with it and get it to do it exactly the way you want it to. So this is kind of a concept piece, because this is, the edit tool for these images is the whisk broom, and off we go and we can print another image. But it was a real aha moment in terms of just completely taking on the production of the object by making the tool all the way up. So when I got to Chrysler and Associates right after doing that project, we commissioned another big mill, and just one of the most interesting things I've got to do was to build this machine that you've been seeing in making these big molds. But again, if you're going to be making a machine that's not particularly precise, you're going to end up, it's pretty interesting what you're seeing here, the commissioning of this mill, it has to be calibrated in the first place before it can mill a perfectly rectangular Cartesian space. So that is like a surveyor's transit. And even with that tool, just an optical transit and a machinist's square, we were able to sight from across the room, like split the 30 seconds on a machinist's square, and then do it across the machine, and so you know the machine is level. And that's about the truest space you'll get. It turns out in the fabrication business, that thing of what is actually flat, what can we measure from in a room that has a rough-hewn floor, like even the steel tables that you'd place down it aren't actually flat. So maybe the first thing you do is put down foam and mill the foam flat. Now you have a table, and now we'll put the thing on top of that. So if you're brave and willing to think your way into and out of lots of problems and willing to take on kind of all that risk yourself, you can do kind of amazing things. And this is that machine in milling away. I put this in there as the counter example. A couple of lessons here. One of them is if you have that sneaking suspicion that something might be dangerous or fragile, I want to encourage you to listen to that voice and to do something about it. This machine had the odd capability that the ball screw for the z-axis couldn't resist gravity, so when the power went out, the mill would plunge. And the switch for the drill bit for the tool would turn on when the power went back on. And so I think it failed sometime during the night and burnt itself up. It actually vaporized some of the aluminum structure in it. That's the temperature at which polyurethane burns. So I don't know, this is kind of an amazing thing to see. So, okay, just a couple more pieces. One of them, I think it's been interesting to see this, like, was it this, the big Delta machine trying to 3D print at scale, right? It's telling you guys. But it's really difficult to build a house or something at that size because you want to do it this pristine thing all in one pass. The truth of it is, I think a lot of the time it's really composite in a general abstract sense. That you're going to make a thing out of lots of things. So here's just a little concept piece, this architectural preservation of this thing. How could we build another one? How could we fix it? Well, it turned out we can scan it, but to fix the scan is really difficult because you can't sculpt in 3D unless, even these haptic things, it's really hard. You don't have any sense of when a surface is fair. Just like you do, you can look at it in the sunlight, and I can tell you if a curve is fair, or I close my eyes and you can feel it. Try and do that in a mesh modeling program, and you'll just never get it. So actually, it was easier to cut it in half, mill it, sculpt the model, scan the model again, and then use the scanned maquette to make a mold, lay some fiberglass up in the mold. But the top is in round, but the top is perfect. So why even do anything with it? Take a silicone mold of the top, and then do like they did in ancient Chinese bronzes, which is to take a piece, cast it, and take the cast piece and put it in the mold when you cast the next piece, and build up complexity. So here you have like 3 or more different mold making techniques, some digital, some really old school. And the back, this is a piece of plywood, just mold onto that. So there's that piece, you know, it's on the porte cochere in front of this hotel. So I don't know if any of you have been to the Denver Convention Center, but this is a project that Chrysler and Associates did for Lawrence Argent. And it's just the most incongruous thing to see, especially driving down the road, one of its legs, like this big chicken leg. The head, by the time it arrived a couple of days later, the truck drivers had like drawn the eyes and the mouth back on the shrink wrap around it. You know, so you build this big, so the thing shows up on site. How did it get there? Well, it got there like this. Well, how did it even get into those pieces? Well, here's one of the panels. And you'll notice it has to be made up of lots of panels. But look where the flange is. The flange isn't at the panel joints. The flange splits the panels because then the panels are strong. So you'll build it one way and then you'll take it apart a different way. So those flanges I showed you at the beginning, this is the inside of the bear. So you've got what you might call a bulkhead in a ship, circular, sort of laying on our back, looking up into one of the bear's legs. So you'll see there's a panel, and it was the panel actually span the disassembly joints. So here's a model of the bear. You might call this the shop drawing. And here you can see the green lines are the grand blocks where it's taken apart, and the black lines are the panel joints that were milled individually. So the black lines become welded together permanently when it's all built. And then the green lines are where it comes apart to be moved. And you know, you're looking at a bear and you're looking at sculpture, but these techniques in terms of how panels go together and how you negotiate like the structural exchange between the panels, it's directly translatable into how you build panels for architecture. But that's actually not the shop drawing. This was the shop drawing. So the first thing that was done was a maquette was milled, and then the shop director said, how am I going to get it apart? And he drew on the model. Okay, this is how we'll build it. And this thing lived in the shop the whole time. I mean, everybody's like, oh, which piece are we? Oh, yeah, you go and look at the model. Oh, we're over here. And I mean, using 3D printing in the construction industry, I think this has been one of the biggest benefits I've seen, actually, is the 3D printed model that lives in the job trailer, because it's way more descriptive than the construction documents in terms of a crew figuring out what are we going to do today, and everybody puts the 3D printed model in the conference table and Sharpies on it. Which is why when you see something like this, you just have to laugh. Because this is the shop drawing, but nobody ever would look at this. This is for show, and because the municipality needs something to put a wet stamp on. And a lot of the time now, this is what's happening, is we're doing the drawings because we need to do the drawings. But actually, the contract now has enough writers in it that you can give your files to the contractor, and actually what he's doing is looking at the 3D model, and they're trying to figure out how they build it. Because we know the architect doesn't know how you're going to build it. We don't do means and methods. Figure it out yourselves. Which is, still don't understand why the architect then reviews the shop drawings, because we're not qualified most of the time. So I'll get back to this issue about the shop drawing, because someone still has to look at this and decide whether it's right or not. And we're in this funny moment where neither the architect nor the contractor is fully qualified to decide whether or not a digital file is right. Actually, a mistake was made. Remember I showed you that transit? I only wish that we had used a transit like that on the machine before all the panels were milled. Because it turns out the z-axis of the machine was ever so slightly canted in 2 dimensions, which meant that it was milling a parallelepiped rather than a cube. You don't know that, so you build the whole thing, and guess what? The bear isn't standing like this. He's actually standing like that. That same transmogrification was built through the whole piece. So after it was put together, it had to get fixed. Fortunately, again, you're going to take on all the risk, and you know how to get yourself both into and out of the problem. So see the string lines? Those represent the ground and the face of the convention center. So then it was mock assembled within space, but you can't actually tip it upright in the shop. You have to lay it on its back and then construct space around it, and then fix enough of the panels so that it doesn't actually lean through the glass. I think we used up our contingency on that. But it's pretty cool to see. Some more ripples in made real. I put this in there again because it's kind of like the fabricator's lesson. So often, the fabricator is the reality up against which the design bumps. This is what the designer saw. This is what I saw. And despite my urgings to turn off smooth shading in your display, I never did get a properly smooth object. So there's the smoothing. It's called a pneumatic orbital sander. Until the point where it had to be sanded that you go through the nice, expensive blue gel coat into the composite behind. So, I mean, it's a good thing that they know how to do some really nice finishing, because then we sprayed more gel coat over the surface and the piece came out just fine after a lot of hand labor. But the lesson is to take the digital seriously, because in digital fabrication, it's not an abstraction, it's an actual thing. Triangles are things. I guess the bear, he's just like lurking in the background always in its pieces. So here's I just want to show this to you because, again, this is another one of those techniques take away with you next. If you're ever making like molds of things, panels that need to go together, here is actually that technique. So the molds were made, flanges were put on after using plywood because it's easy. Why mill that stuff? A piece of like flashing from the hardware store, you can slide it down into the foam. There's an instant flange with little blocks of foam as keys to lay that up. When fiberglass cures, it shrinks, and you'll get like 15 degrees that the flange wants to pull back the one direction. So lay the next panel up against it, and you've absorbed at least half of that flex. So now you're down to 7.5 degrees. And that's within the range with which a bolt can just cinch the two panels together, and actually nicely tension one against the other. So there's the how-to of actually molding panels. Little embed fasteners. Thread in after the fact so that you can stack the piece without it scratching another piece. This kind of ridiculous drawing that looks like it should be a shop drawing but was ignored the moment it was shown because it shows neither how to build it nor really what it's going to look like. This, the actual shop drawing, which is just like Rhino. How to measure, the shop drawings had angular measurements of them, but to the fabricator that's like useless because angular with respect to what? One of the orthographic planes, like that's not useful. I need to know with respect to the fold, right? So leave me a coordinate system in the model that I could look at to see. What actually we ended up having to do was to draw them all so that we could build a custom crate for them to ship it. Again, it's one thing to build something, it's another thing to get it on site. Even at scale, that's still the same thing. So I'll leave you with this project. This was the sculptor is actually an ad exec by day. He's the one responsible for the king, the creepy Burger King head. That's his ad campaign. So it was a concretization of light, is the sort of this piece. In building it to be assembled and then disassembled, there's some really nice details in it, actually. How these panels come together. There's an in-bed system with a post-tension chain, so you can reach into the piece and then latch one panel to the next. So there are the tendons that run through these tubes that are cast into the piece. So here's that lesson again. So we get this model, and we're going to build it. And here, do it just like this, and here it is, and you look at it. But who's going to go over every last triangle of a mesh? I mean, the same thing can be true of any kind of digital representation of a building that's ever detailed, where we get down to the level of the return on the flanges of something. Like a triangle doesn't tell you who looked at that triangle to say that it was in the right place. Increasingly, that kind of, you might call it PMI in the mechanical space, the manufacturing information, that's like managing the whole information chain on stuff. Increasingly, models can become information rich, and I think it's one of the promises of BIM in a way. But we've got a long way to go, and this is just a perfect example, because when you actually looked at it, these were overhanging, and the triangles were like an inch in size. And so really what they do is they just shadow. If you're going to do 3-axis milling from the top, you just ignore the overhang. And so long as you can get signed off on it, that's cool. So here's just that thing at scale. Oh yeah, it was actually, this was the first time I used generative components to try and do fabrication planning. The aesthetic of this should show you what year it was. GC is a precursor to Grasshopper and Dynamo. It's kind of nice if you can capture the flanges around things. If anybody's done milling, you know, as soon as you roll off the part, the drill bit wants to plunge, and when it does, the collet's going to collide with the part. So you have to make these nice, gentle slopes around things, and that is really labor intensive if you have to do it manually. So why not capture that logic and just apply it algorithmically to the part? So that's what we did, and wrote out so many tool paths in this big machine. These molds, you have to lift them off with a crane. And a lot of aluminum foil. Again, just matching the level of the cost of the material and the level of accuracy to the project. So I put this in there because I only wish this is what you get, right? Like vacuum bag these big things, and you can't smell the resin or anything, and just resin goes through the cloth, and like boom, you got a part. But actually, a lot of fiberglass composites most are done this way, which is the resin is being applied using rollers and paint brushes, to mop up the extra resin till you can compact it, and it's really high touch. High touch and high tech, because the other thing is that you couldn't ever make these kinds of molds at this size if you weren't milling them. I mean, it's interesting that it's really this high tech kind of digital fabrication that is unlocking composites for use at scale. And just some shots of the piece being put together, all these little tabs, like some kind of dental operation, fixtured in place until it was kind of all seamed together. It had a post-applied stucco. interesting thing about composites is you really, you don't have to mold these perfect surfaces into them. You can do all sorts of stuff to them. So just finish with this. Couple shots of it installed. Thank you.